Hello dear students. Today we are going to start the new article, that is Fermi's golden rule. Till now we are aware with the basic structural arrangement of semiconductor. There is a valence band at the bottom level, conduction band at the topmost level, and in between there is a energy gap, that is the band gap. So what is the probability for an electron in the valence band to travel towards the conduction band by gaining some amount of energy? So, in given particular time, how many electrons can be travel from valence band to conduction band? In order to identify, we will have the Fermi's golden rule, which is also referred as golden rule of time dependent perturbation theory. This is nothing but an equation for calculating the transition rates. The result is obtained by applying the time-dependent perturbation theory, which is a well-known theory from quantum mechanics, to a system that undergoes a transition from an initial state I to a final state F, that is a part of continuum of the states. Time-dependent perturbation theory is utilized to calculate the transition probabilities. So, here we will identify how many electrons in a given time can transit from initial state I to final state F. So, in order to initiate the theory, we will start with the Hamiltonian equation. So, we assume that the Hamiltonian H of the system can be written in the form of H is equal to H0 plus Wt. This is the equation number 1, where H0 is the Hamiltonian of unperturbed system and Wt is the time dependent function of the perturbation applied to the system. Since H0 is the unperturbed Hamiltonian, the time independent Schrodinger equation is satisfied as H0 psi is equal to En psi. So this is equation number 2. H psi is equal to E psi. That was the general Schrodinger equation, and for the unperturbed Hamiltonian we can write down equation number 2. The wave function phi n are related to the time dependent unperturbed wave function by equation number 3, that is psi n of t, which is a time dependent wave function, is equal to phi n e raised to minus I en t upon h cut. This en is the energy at the initial state, t is the given time, h cut is equals to h upon 2 pi, where h is the Planck's constant. The time dependent Schrodinger equation for the system is h psi t is equal to, according to equation number 1, h0 plus wt is equal to I h cut del psi by del t. With the state of the system wave function psi at a time t expressed as a linear combination of the phi n basis function. So now we will modify this particular term into the basis function. So here you can see this psi t is now converted into the summation of cnt psi nt is equal to summation of n cnt. Instead of psi nt we are utilizing equation number 4, cnt phi n e raised to minus I ent upon h cut. This is our equation number 5. Substituting this relation in equation number 4 and project the result on phi n. So what was the equation number 4? Here h0 psi t plus wt psi t will be now separate out. So h0, instead of psi we have carried out this term, but instead of n we have taken particular wave vector k. So in the three-dimensional space, or you can say the reciprocal space, we can have the exact position probability for an electron to travel. So summation over k ckt phi k e raised to minus ekt upon h cut plus wt summation over k ct phi k into e raised to minus ekt upon h cut is equal to I h cut del by del t summation over k ct phi k e raised to minus I e k t upon h cut. This is the equation number 6. Summation over k ct ek phi k e raised to minus I e k t upon h cut. This simplified this equation, okay, where h0 has been divided from all the sides, plus summation over k ct wt is now inside the summation phi k e raised to minus ekt upon h cut is equal to, now we are differentiating this equation, differentiating the right hand side. So I h cut is as it is, summation over k, the first term differentiation, so del ct by del t into phi k e raised to minus I e k t upon h cut. Now first term will be as it is in the differentiation of second term, so plus I h cut summation over k ct phi k minus I e k t upon h cut, the power comes into the multiplier and hence the remaining term is exponential minus I e k t upon h cut. This is equation number 7. Simplifying the equation, we will get en c n t e raised to minus I e n t upon h cut plus summation over k, this term is as it is, ct w n k t e raised to minus I e k t upon h cut is equal to I h cut del c n t by del t e raised to minus I e n t upon h cut plus en cnt e raised to minus I e n t upon h cut. This is equation number 8. So you can see the difference where the ct function, the summation is almost carried out and the remaining terms of phi k are eliminated from equation number 7. And this equation is further classified as, because this term and this term on the left hand side and right hand side are similar, so they will get cancelled out. So the remaining portion is the equation number 9 as summation over k ct wnkt e raised to minus I e k t upon h cut is equal to I h cut del cnt by del t e raised to minus I e n t upon h cut. This is equation number 9. From this equation we can moreover simplify by making del cnt by del t as an object. So I h cut will go into the denominator, that is equal to 1 upon I h cut, summation over k as it is, ct as it is, wnkt as it is, and by combining these two terms minus I ek minus en, so we will have e raised to I omega nk t, where the perturbation matrix element is now simplified as 2 pi en minus ek upon h, where h upon 2 pi is nothing but h cut. In order to evaluate the coefficient from equation number 10, remember this is the simple equation we have derived, but still we have not ended up to the mathematical expression of Fermi's golden rule, which is a time dependent perturbation or possibility of transition rate. So for that we will have to solve this equation, and here in order to evaluate their coefficients we are making two assumptions. Number 1, the system is initially in state I, and thus all the coefficient at 0 time are equal to 0 except for the c coefficients, that is equal to delta ij. The perturbation, that is the second assumption, the perturbation is very weak and applied for a short period of time such that all of the coefficients remain nearly unchanged. So at first we are assuming that at t is equal to 0 all the coefficients are 0, and at the second assumption we are assuming that due to weak perturbation there is no change in the matrix coefficient. So we will have this type of equation by applying these two assumptions, del C and T by del T is equal to 1 upon IH cut CIT, that means in the initial state, WNIT. So instead of K, all terms are replacing with the initial state term I. WNIT e raised to I omega NIT. So for any final state, the coefficient will be CFT is equal to CF0 is equal to 0, and hence for the final state CFT is equal to 1 upon IH cut. In order to remove the differentiation over here, we have integrated both the sides of equation 11 with respect to time. So 1 upon IH cut integral 0 to t WFIT dash e raised to I WFIT dash into dt dash. This is the equation number 12. So here the time has been changed because when the electron is in the initial state, that is at time t, but when it has traveled to the final state, the time will be changed, and hence we have denoted the final state time as t dash. Application of the perturbation changes the state of the systems from the initial state phi I to a final state phi f, both of which are the eigenstates of the unperturbed Hamiltonian H0. The probability of finding the system in the eigenstate phi f is equal to rho IFT is equal to phi f psi t square. So this is the matrix function. Moreover, when the final state is part of continuum of states, that is, when the energy belongs to a continuous part of the spectrum of H0, we must have to take in account for all the states to which the systems can jump to. That means, in between the initial and final stage, what are the intermediate possibilities where an atom or molecule or your micro level electron can transit. This is done by integrating the probability as given by equation 13 in the earlier slide with the density of states as weights. So we have integrated rho t is equal to integration of energy rho IFT rho e into dE, that is the equation number 14, where E actual denotes all the states of the system that can jump to under the influence of perturbation, that is the accurate energy. The probability function is sharply picked at omega is equal to omega fi, and as a result acts as a delta function in the integral, and thus selects the value for the density function at omega is equal to omega fi. You can see the pick from the probability function with respect to various frequency, and this is the density of states function, where we can easily write down rho t is equal to integration E accurate wfi square upon h cut square with the density function of t omega minus omega fi rho e dE, which ended up like this, is equal to integration E accurate wfi square upon h cut square sine omega fi minus omega t by 2 divided by omega fi minus omega by 2 whole square rho e into dE. As can be depicted from the figure, the range of energies is very narrow, and as a result the matrix element wfi and the density of states can be considered as constant. So this particular variation has now been analyzed as a constant. So rho t is equal to wfi square upon h cut square rho efi integration over E accurate sine omega fi minus omega t by 2 divided by omega fi minus omega by 2 whole square into dE, that is equal to wfi square upon h cut square rho efi integration over accurate energy sine omega fi minus omega t by 2 divided by omega fi minus omega by 2 whole square. Now instead of dE we have written h cut into d omega. This is nothing but the simple relation E is equal to h mu is equal to, more simplifying the equation, or we can say the integral term has been normalized. Wfi square upon h cut square rho EFI into h cut into 2 by t into t square integration from minus infinity to plus infinity sine square x upon x square into dx, where we substituted E is equal to h cut omega, x is equal to omega fi minus omega t by 2, and we have utilized the fact that for frequencies far from omega fi, the function sine square x upon x square is negligible. So we can extend the limits towards the infinite. The value for the integral is well known and it equals to pi. So rho t is equal to 2 pi upon h cut wfi square rho EFI t, that is the equation number 16. Equation number 16 results is significant in that the probability has a linear dependence in time, from which the transition rate can be calculated like this: W is equal to the differentiation of equation number 16 with respect to time is equal to 2 pi upon h cut wfi square rho EFI, because dt over dt will be cancelled out, and that is the equation number 16, which is known as the mathematical expression from Fermi's golden rule. This equation states that in order to calculate the transition rate, all we have to do is multiply the square modulus of the perturbation matrix, that means the probability of electrons in different transition states between the two states, by the density of states at the transition frequency. So this was the detailed explanation of the theoretical model of Fermi's golden rule, with which the transition probability can be easily evaluated. So thanks for visiting this lecture.